And I don't know how many of you here saw the film The Singularity is Near, Ray Kurzweil's film. Did you see the documentary? Well, it really was quite stirring, and when you listen to Ray Kurzweil and what is coming down in the future, the computers are going to rule our lives and avatars and research, and I was thoroughly fascinated by it. And then Watson won Jeopardy. And somebody said, who would you most like to have as a dinner partner these days, Marianne? And I said, Watson. Well, that's not going to be so easy. But we have Bhavani Iyer here today, who worked on Watson and on the team that helped Watson win Jeopardy. And when we look at all the work that we're doing in the life sciences, I think it's extremely important to recognize where the computers are going to play a part in advancing our research, and also to find out how Jeopardy influenced Watson, how Watson influenced Jeopardy, and what Watson's going to mean to the future of health research and health care. Thank you so much for joining us today.
It's a pleasure to be here. So I'm going to give a brief overview of the IBM Jeopardy Challenge. So I guess this is the entertainment section of the program. So as many of you probably know, early in February of this year, Jeopardy Productions aired a two-game matchup again between the two all-time champions of Jeopardy, Ken Jennings and Brad Rutter, and a computer system called Watson, but is built by IBM Research. So I was fortunate enough to be a member of that team, and it's probably one of the most exciting projects I've ever been on. So as you can see by the scores, Watson won pretty commandingly, and this was really a milestone in an area of research called automatic question answering. And it's really brought a lot of attention from both the scientific community as well as the general public. So I thought I would just cover a few points about the project. One is why it is a technical challenge, and describe the problem that we were addressing, and what it took to build Watson in terms of how does Watson answer the question, how to make Watson fast and a competitive game player, and the development approach we took. And my contribution to the project was in the building the system, scaling it out, and the performance optimizations. So basically the making Watson fast segment of it. So I'll also briefly touch on the future work that we are planning to do. So why did IBM undertake this challenge in the first place? So IBM has a tradition of undertaking, trying to sort of assess and know whether we're actually making progress in key technical areas. So, and in this particular, for example, in this case, it is what's called open domain question answering. And to also demonstrate that we can use the technology to solve very concrete problems and tasks. So the Jeopardy is a well-regarded and highly popular game show that airs 5 days a week, and the contestants on the show are expected to understand and answer questions on a pretty wide variety of topics. So this provided a compelling opportunity to advance and to this area called open domain question answering in a number of key aspects. So one is obviously it's a wide variety of topics. As you can see, a particular game has 2 rounds where there are each round has 6 categories, and each category has 5 questions. So within a game, you have 60 questions plus an additional final Jeopardy question. So these are just cover any range of topics. Secondly, the questions are written in complex language. So they're written by for humans to understand. It's written for entertainment, so it's supposed to be fun. There are puzzles and puns and so on. So it's not a straightforward questions of facts. So and here are a few examples. So they're like, for example, the first category here is colorful books for $100. It was Alice Walker's third novel. Does anyone know? Color Purple, yes. And another question is biology, which I'm sure everybody here knows. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid, cushioning the nucleus. Yes. And diplomacy, of the 4 countries in the world that the U.S. does not have diplomatic relations with, the one that's for the farthest north. Yes, very good. Okay, so the third aspect of this problem is high precision. You have to deliver one answer, and it has to be the correct one. And another notion here is the accurate confidence. So what that means is that you have to know what you know. So if you're unsure of the answer, or because there is a penalty to giving the wrong answer, you get deductions and points. And finally is high speed. You have to be fast on the buzzer to get the chance to answer the question. So these aspects of the problems were gave us really it's primarily the complexity here comes from understanding the question and finding the right answer and doing it fast. So there's the idea that some people try to approach this problem by trying to build databases that are very specific to certain topics. We do not take that approach. That is simply because it's impossible to anticipate all the possible topics and what kind of questions will be asked about that topic. So we did a study of some 20,000 questions. And basically, we found that 13% of those actually could not be typed. And of the remaining 87%, they really could be spread around 2,500 different types of topics. And none of the topics, if you look at the vertical axis, no topic really took more than 3% of the questions. So this approach really would not have worked. So it was necessary to sort of dynamically determine what the question is asking and find the answer. So here's another type of question where some questions require decomposition and then resynthesizing the things. Here's a question: it says, a long, tiresome speech delivered by a frothy pie topping. So yes. So again, you have to break up the question into 2 parts and answer the 2 parts, and then you will see that, and then resynthesize the answer. And you'll notice here that we have had to flip the order of the words that to be different from the order in the question to get to the final answer. Here's another example where, again, you can. This is to illustrate that you can't just take the keywords in the question and then do a search and get the answer. You really have to decompose it and take the different parts of the question and possibly look it up in different sources to get to the answer. So when 60 Minutes premiered, this man was U.S. president. So we break it up into 2 parts. When 60 Minutes premiered, and some sort of temporal analysis has to occur here to determine that this was actually in 1968, and then take those 2 additional pieces of information now that you have and find the final answer, which is Lyndon B. Johnson. So the Deep QA architecture, the Deep QA is the technology behind Watson, attempts to do this, decomposes it, and reapplies, sort of recursively applies the algorithms to each of the parts and then combines them to get the final answer. So, so humans are really good at this stuff. They do it instantaneously, and it's sort of effortless, and they know what to do. But however, this chart, for example, shows the best human performance on this. So each dot here represents a Jeopardy game, and it represents the performance of the winner of the game. So you'll notice here that, well, they answer about, they get to buzz in and answer 50, at least on average, 50% of the questions, and their accuracy and precision is really up close to 90%. 85 to 90%. And the red dots here represent the performance of Ken Jennings, who was the all-time sort of champion of the game. And he is like, he knows everything, and he's very fast. So this is sort of the goal that where we had to be. So and the brown line below, well, shows the initial performance of Watson when we started out on the project about 4 years ago. So we had quite a bit of work cut out for us. So how does Watson answer question? So just like human beings, Watson has to study. In the game, in the actual exhibition match, we were not allowed to go on the internet. We had to, so that means one of the aspects of this project was to collect different sources of information, documents, news articles, dictionaries, Wikipedia, and all sorts of information, and sort of find these sources. They're both structured and unstructured. And what does it mean to say that Watson studies? It basically means there are algorithms that go and read the text and extract both syntactic as well as semantic information from the text. For example, subject word, grammar, and then there are additional algorithms that go over the syntactic frames and extract semantic information. And then these are then tied to structured databases and ontologies, so that we can now link it to some additional information. So, so here I'm going to just walk you through how Watson actually answers a question. So this question is, in 1698, this comet discoverer took a ship called the Paramore Pink on the first purely scientific sea voyage. So Watson first has to, the system first has to understand the question, and it does so by decomposing it into keywords. It does some other sort of temporal analysis to see if there's a date, finds relationships between words. It also decides what is the focus of the question, which here is called the answer type. Here we're looking for a comet discoverer. So using this, it does sort of a broad-based search on our content. And so there are multiple queries that are issued, and we try to retrieve documents as well as sentences and passages, as well as titles, and so this is multiple searches are done to acquire the relevant content that is relevant to this question. Once we have that, we go through this process called candidate answer generation, where there are algorithms that go over that to say what are the phrases and words in the retrieved information that could constitute an answer to the question. So these we term as hypotheses, and we hypothesize that that any of these could be potentially answered to the question. And then we go and say, what is the look for evidence, additional evidence for each of these potential answers, which again involves doing another set of searches and linking up to structured databases and so on. Once we have this additional information, a number of algorithms components attempt to see how much of a fit is that candidate answer with respect to the question, and how much of a match it is. And this evidence is evaluated across multiple dimensions. It could be lexical, taxonomic, spatial, temporal, and so on. And each candidate is scored with respect to each of these dimensions. And as a final step, these are fed into a model that sort of weighs the different scores and produces a final score for each of the candidate answers and ranks them. And then we compute a confidence, which then is used to determine whether the system should actually attempt to answer and buzz in and get it and actually answer the question. So this whole thing is made possible by the fact that we have an architecture which allows multiple components that are loosely coupled to interoperate. And this has also been a big plus in enabling us to extend this to other domains. So here, another aspect of this is was not used in the in the match. But in addition to actually giving us a final answer, the system is actually maintaining information about the evidence with respect to each of the potential answers, and we could drill down. We use this to debug and to sort of understand why the system answered in a particular way and to improve the system. But for example, in this clue, Chile shares its longest land border with this country. There are two candidate answers that were. This allows you to compare two candidate answers and why one was weighed more than the other. So here you have two candidates, Argentina and Bolivia, and you will see that with respect to classification, they are both classified. They are both countries, so they get the same scores. But you'll see that with location, Argentina has a higher score, possibly because that's some sort of a geospatial analysis that has taken into consideration the phrase longest land border. And if you notice with popularity, you actually have Bolivia as getting a higher score simply because there may have been some event that occurred about Bolivia that we have a lot of information on in our database, in our sources. So this is a kind of an important aspect of the system that when we do new applications in healthcare or any other domain, and in sort of decision support system, it helps you to the end user to see why a particular answer may be more relevant or important or why certain evidence was given more weight. So this shows basically how we improved the system over a period. So basically, we worked on the project from 2007. And you can see that we made steady and incremental progress. And finally, when we were close to the exhibition match, we were performing at grand champion levels. So this was actually the work of about 25 researchers and software engineers. Most of us were based in New York. There were about 130 different components, and it was very much a measurement-driven process where we would essentially, on a week-to-week basis, measure how we were doing on the system. Though you could, the architecture allowed individuals to develop components and improve components, but before you could integrate it into the system, you had to demonstrate how it added to the system and what impact it had on the system, and so there was extensive experimentation. We were fortunate that we had access to past Jeopardy questions as well as answers, and we could use that to train the system as well as to run tests. There was a huge amount of engineering support as well. We had the individual developers were running experiments as well as we would have these integrated weekly runs and monthly integration, and that all required a whole bunch of tooling and management. Making Watson fast. So obviously, to be a competitive player, you had to be fast because only the first person to buzz in gets to answer. On average, you basically get. So the way the Jeopardy game works is a clue is revealed, and Alex Trebek, or the host, reads the question, and the buzzer is opened for the contestant to buzz in when he finishes reading the clue. So on average, that took about, for most questions, it came in at under 3 seconds. But initially, when we started a question would essentially take us on a single computer. On an average workstation was taking us an average of 2,300 seconds. And many questions were actually taking us well beyond that into, a couple of hours to actually process the question. So obviously, we had to find a way to scale this out and get it down to a competitive level. So here is at a very high level the the architecture of the system and the flow. So what we did is basically instrument the whole process. We computed on average what are the work items that are being generated at each level of the processing. And we also determined that it's very much a scalable system because once the question was analyzed, each of the steps in the process, like candidate, searching or candidate generation, evidence gathering, and scoring, the components could essentially work independent of each other, and so it was a very highly parallelizable system. And it was also built on an open source framework called UIMA, which stands for Unstructured Information Management Architecture, which had within it a component called UIMA-AS, which stands for Asynchronous Scale-Out. So both UIMA and UIMA-AS were actually projects initiated in our group, and which we then open sourced. So using these technologies, we were quickly able to scale out the system. But the other aspect of it was the amount of data we had. We had we were taking 65 gigabytes of raw source and indexing it and pre-processing and pre-computing the NLP, running NLP processing on it, and all of this data had to also be scaled out. So we had to basically break down the data into chunks and spread that out and be able to access the data in parallel. So with these, scaling out the components, distributing the search, pre-computing, and doing the NLP analysis, and making sure that all data was in RAM and so on, we were able to get the system down to performing at on average of 2.6 seconds per question. And I think just about all questions were answered within 6 seconds. So this is the system that actually then, the final system was run on a IBM Power 7 cluster. It had 2,880 cores and 15 terabytes of memory. And prior to the games, we actually ran a number of what are called sparring matches. We invited contestants who had actually been on the show to come and compete against the system. These were actually tournament of champion level players. So we ran about 55 rounds of games, and Watson came in first place in 39 of them, which is about 71%. So this was the system we were at going into the game. So I want to just touch briefly on some of the... so anyway, this had a huge impact on the mindset of people, and there were a number of applications, requests coming into the group. And I think what we have chosen to do is really focus on healthcare and life sciences. So this is going to be a little different from what we did in Jeopardy, where in Jeopardy we actually had to pick the right answer and present and deliver that. Here it's going to be quite different in that what we are going to do is support decision making by basically presenting the options and presenting the evidence that backs up the hypothesis. So we sort of have partnered with companies that are in the clinical decision support business and sort of doing sort of evidence-based medicine and differential diagnosis. So one sort of scenario where we see this working is in this differential diagnosis. So here you see in this chart, possibly 3 possible diagnoses, and you see these dimensions of evidence in the chart. So whether it's coming from symptoms, the support for each of these hypothesized diagnoses, coming from symptoms or family history and demographics, and it allows the user or the clinician to drill down and find out where is the evidence actually coming from, like the textbook sources or guidelines or whatever. So we envision the system being adapted in sort of multiple ways. Obviously there's going to have to be new algorithms to understand medical text and processes, and then how to actually bring this into a clinician's workflow without actually being intrusive and obstructive, I guess. Another aspect is content adaptation, which is what I'm sort of focused on, which is bringing in new content, new types of content, which is medical textbooks, guidelines, patient records, and so on. And there are additional problems here because we want to be able to have when we ingest content, we are actually transforming it and changing its representation, but we need to keep provenance so that we can track it back to the original raw source. We also need to be continuously ingesting content, as patients' records get updated or there's new guidelines being posted or whatever. So these are sort of new aspects of the problems that we are now sort of looking into and hoping to address. And finally, I wanted to show you this. We have been experimenting with these doctor dilemma questions that you might be aware of. This is sort of the doctor's version of Jeopardy, I guess, which is used to train medical students, I believe. So we have taken a subset of those questions, and we are trying to see how we do on those questions we started with our original, the Jeopardy system, and now we've added content to it, some open source available medical content, and retraining the system and so on. And we're making sort of incremental progress there. So, that is where this is headed, I guess. So thank you. So this is the team of people. Including, the core team is really the systems and the algorithms team that are based in Hawthorne. And that is an IBM Watson Research Center. So we also collaborated with universities, specifically CMU and UMass. And and now we have sort of more commercial partners coming in. Thank you. Question? Yeah. Oh. Okay, go ahead.
I have a question. Are you looking for more university collaborators in the life sciences?
Yes, we are looking for university collaborators.
Are you the person to contact for somebody who's in a lab and wants to do something that perhaps...
The person to contact will ultimately be Dave Ferrucci, and possibly another person, Eric Brown, who handles university relations and so on. Yeah.
Simple question, but I obviously missed it. What was the answer to the comet discoverer question?
Haley.
Haley. Yeah, that was my vote. I didn't get it. Thank you.
Oh, sorry. Okay. Yeah, Edmund Haley.
So there's been a lot of work on the bias of physicians in terms of gender and to some degree race in their diagnoses and treatments. I was wondering if Watson is going to be an answer to that, or do you think that's more due to the data going in?
So I think it's going to have to be the data going in. It's the system is very much there are two types of data. One is training data. So obviously, in the case of Jeopardy, we had questions and we had example questions, and we had thousands of questions and answers. And then we had data that from which we could, that we sort of read and understood to try to answer the question. Yeah, so it is very much dependent on the data that is fed to it on the two ends. It's not going to be something that's... Well, one thing you can provide is training data that is specific to women's issues or medical conditions and so on. And if you can, that would certainly be a sort of a sub-project that's a specialized use of Watson. But again, it would depend on someone providing information to support that.
So some of the research says that it's how women express themselves in a doctor's office that may affect the doctor in a way that leads to a different diagnosis. So will Watson also be sensitive in that way to how patients talk, or will that be somehow...
Watson would have to be trained. Essentially, that's what it is. Watson has to be trained. So if you provide patients who are of a particular gender or a race or whatever it is, and if you can then have information about conclusions drawn about from those records, and then we could make correlations and trace things and be able to take that into consideration. Yeah.
To what extent do you think Watson is still limited by natural language understanding? For example, how differently does Watson perform when Watson's able to read answers or have questions typed versus having to understand the natural language orally?
So Watson never understands anything orally. Everything is typed, but it is typed as natural language in the sense that it's a text message that it's given to it, but it is expressed in natural language. So it is, yes, it's highly dependent on how well it understands the question. It also is highly dependent on, whether it has accurately read the background knowledge that, in textbooks and so on.
So how do you feel that's going for further work? Do you feel that Watson or a system like Watson will be able to understand spoken language?
Spoken language is a sort of a speech recognition problem, yes. So there's a separate group working and specializing in that. Again, that's also a work in progress, yes. But I think the bigger challenge here is understanding, as for example, like we haven't really done a whole lot of work on negation. So, okay, when something is not this, and which you might find a lot in a medical situation where somebody does not have this or does not exhibit that. So those kinds of expressions, we have to train the system to recognize and understand.
Hi. Can Watson understand medical records and extract useful information from unstructured reports, if you will, and can it even take in images into consideration since there's a lot of computer-assisted detection and diagnosis already?
Right, so far we have been focused on unstructured text. And we have been working with, open domain sort of, general topics. So now we are trying to specialize, to make it specialized to medical or, like help desk kind of application and so on. Yeah, we haven't really explored image and that kind of audio and records as yet.
And I guess related to that, can it get feedback if it spits out an answer and then 2 weeks later the patient's diagnosed with X disease, does it learn from that?
So we did have some degree of learning within Watson. So for example, if it was answering a particular category of questions and was consistently getting it wrong, it would learn from that, from previous errors, yes. So yeah, one of the other projects that is going on is something called Teaching Watson. And Teaching Watson has two connotations. One is using Watson to teach and use it as an educational tool. And the other aspect of Teaching Watson is to help it to be trained. So we kind of did something similar to this in a project involving machine translation, where this was a real-time translation service that I worked on before I did this, where this was for telecommunications kind of businesses, where you would have a text message in one language and it has to be translated and delivered to somebody who's in some other language. So what we did there is once you typed a text message, it would present the translation so that you could fix it, and then the system would learn from those corrections. So that kind of thinking, yes, is there, and we are planning to pursue that.
One more.
So some people feel that medicine may go in the direction of having individual genome sequences available as genome sequencing gets cheaper. Is there a project ongoing to sort of interface this with that kind of information?
No, we haven't. I mean, I don't. I'm not aware of a specific project, but there are groups working on genomic information and so on. So. Again, we are sort of limited by the fact that it has to be commercial and customer for these things. So it would, and we are also looking to partner with people who have data and are willing to help us to train the system.